Hi everyone, I'm Sumeira. First, let me thank the organizers of this topic group, which is Knot Surfaces and Form Manifolds. Thanks for organizing this session and for your invitation. It's a great pleasure for me. Let me also thank the organizers of this conference. I'm sure it's gonna be fun 2 weeks. Now let me begin. I will talk about one of my recent work, and my title is Symplectic Form Manifolds on the Noether line and between the Noether and half Noether lines. And in fact, my preprint is on the archive. If you are wondering for more details, you may wanna check there. Well, this talk will be about constructing exotic form manifolds. So first, let me give some definitions. Exotic manifolds are smooth manifolds that are homeomorphic but not diffeomorphic to each other. So they are topologically the same manifolds, but their smooth structures are different. During my talk, by the way, most of the manifolds will be smooth, closed, oriented, and four-dimensional. And on the other hand, a symplectic manifold is a smooth one with a closed, non-degenerate differential two-form omega. And therefore, the symplectic manifolds is a restrictive class inside smooth manifolds. It is more restrictive, but it is richer. In the existence of this extra structure, we have more tools, more techniques to work with. And in fact, in the literature, there are lots of different exotic form manifold constructions, and they could be either symplectic or just smooth. But here, let me give just one of them. Ahmedov and Park constructed an exotic form manifold, which is an exotic copy of complex projective plane blown up at 2 points. And today this is the smallest known exotic form manifold. By small, we mean that the Euler characteristic of the manifold is small. And we have some open problems. For instance, we don't know whether there exists an exotic copy of the four-sphere S4. And the conjectural version of this question, which says that there is no exotic S4, is known as the smooth Poincare conjecture. And similarly, you can consider the symplectic category. We don't know whether there is an exotic CP2 or exotic CP2 blown up at 1 point or exotic S2 cross S2. These are all open. And let me briefly talk about this last question here. The existence of exotic S2 cross S2 is open, but there is a progress in that direction. Instead of this manifold, let's consider this guy. So here, this denotes the connected sum of n copies of S2 cross S2. And recently we proved the following. This is joint with Ahmedov and Park. We showed that there exist infinitely many symplectic and non-symplectic exotic copies of n S2 cross S2 for n is an odd integer and n is greater than or equal to 27. And in fact, this result previously it was known for n is at least 175, and here we made much smaller constructions. Note that n is B2 of the manifold, therefore our manifolds are smaller than the previously constructed ones. Now let's consider another type of problem. Instead of considering small exotic form manifolds, let's consider this problem. Let's say that we have a closed, simply connected symplectic form manifold X, and E of X is the Euler characteristic, and sigma is the signature of the manifold. And a pair of numerical invariants are assigned to X. First one is chi h of X. This is called the holomorphic Euler characteristic. And the second one is C1 squared of X. This is the square of its first Chern class. And they satisfy these two equalities. And we have a plane, chi h C1 squared plane. And it is called the geography chart. So consider this chi h as your x-axis and C1 squared as your y-axis. And then on this chart there are some special lines. I will give two of them here. The first one is C1 squared is equal to 2 chi h minus 6, and it is called the Noether line. And the second one is C1 squared is equal to chi h minus 3, and it is called the half Noether line. And in fact, for minimal complex surfaces of general type, the Noether inequality holds. This means that such surfaces, they are all lying above the noether line on the geography chart. Moreover, each such surface has exactly one Seiberg-Witten basic class up to sign. Therefore, we naturally ask the same question for four manifolds. We ask whether we can construct simply connected smooth or symplectic four manifolds with just one basic class. And my work is related to this problem. And in my work, I have used certain symplectic operations. These are called star surgeries. Let me give the main idea of that operation. So, Karakurt and Starkston introduced these surgeries. These are symplectic cut and paste operations in dimension 4. So, the main idea is as follows. Let's say that you have a symplectic 4 manifold, and inside your manifold you have a star-shaped plumbing of symplectic 2 spheres. And then you are cutting out that plumbing from your manifold, and you replace that with its convex symplectic filling, which has strictly smaller Euler characteristic. Therefore, at the end of the operation, you are getting smaller four manifolds, which are also symplectic. And also, Laura showed that infinitely many star surgeries are not equivalent to any sequences of generalized symplectic rational blowdowns. There are some star surgeries, and they are equivalent to some sequences of generalized symplectic rational blowdowns, but infinitely many of them are not. And let me now state my main result. I showed the following. I showed that there are minimal simply connected and symplectic four manifolds on the noether line and between the noether and half noether lines. And they are constructed by using various types of star surgeries and complex singularities. Moreover, each of our manifolds has just one Seiberg-Witten basic class, and each of them has an exotic smooth structure. And in the rest of my talk, I will give the details of, or just sketch of the proof of my theorem. But before that, I need to give some facts. Let me mention them at first. In fact, in the literature, there are different constructions of our exotic four manifolds having the same topological invariance. However, here I give a different construction, and I don't know if my manifolds are diffeomorphic to the previously constructed ones or not. And in fact, giving different constructions of smooth or symplectic four manifolds with the same invariance is an active research area. However, as of today, it is not known how to distinguish the smooth structures of symplectic exotic four manifolds that have the same topological invariance, but they are obtained in different ways. And it is an interesting question. Now, I will give the sketch of the proof of my theorem. For that, I need to introduce some notations and conventions at first. I need to mention some conventions. It is known that blow-ups and blow-downs can be done symplectically. This is thanks to McDuff's result. And here we perform all the blow-ups in the symplectic category. And a notation. I'm working with a specific type of singularities. These are called IN singularities. And the IN singular fiber, for n is at least 2, is a configuration of n complex 2 spheres of self-intersections minus 2 arranged in a cycle. And it was given by Kodaira. And this is the picture of such a singular fiber. These are called necklace type singularities. For instance, if you look at Kirby-Melvin paper, on that paper, they are giving a nice table, and they are giving topological descriptions of all such singularities. And another notation, E1 is the elliptic surface, which is CP2 blown up at 9 points, and En is the n-fold fiber sum of copies of E1. Therefore, we are taking n copies of E1s, and then we are taking their fiber sums. And En is scalar, therefore it admits a complex structure, and it is also symplectic. Well, on my constructions, I have worked with the configurations of IN singularities in the rational elliptic surfaces. So what kind of surfaces these are? Well, a rational elliptic surface is RE1, which is CP2 blown up at 9 points, and it admits an elliptic vibration over CP1. And if it is Jacobian, then it means that it admits a section. And when we say a cubic pencil in CP2, it is a one-dimensional linear system of cubics, and it should have 9 base points by Bezold. And by blowing up the base points of a cubic pencil, we obtain a rational elliptic surface. And the exceptional divisors of square minus 1, coming from the blow-ups, they are corresponding to the sections of the surface. By the way, when we say surface, we mean a complex surface. And moreover, we have this result. This is due to Miranda and Persson. They showed that every Jacobian rational elliptic surface is the blow-up of the base points of a cubic pencil. And when we drop the assumption of being Jacobian, then a rational elliptic surface is still a blow-up of CP2 at 9 points, but in this case the blow-ups are not necessarily at the base points of a cubic pencil. The blow-up points might be different. And as far as I know, at first Naruki explicitly constructed configurations of singular fibers in rational elliptic surfaces by blowing up cubic pencils, and later Persson gave the complete list of singular fibers in the global elliptic vibrations on E1, which is CP2 blown up at 9 points. And another background, in my work I have worked with Seiberg-Witten invariants. Let me give a brief summary of them. Let's say that I have a smooth closed oriented form manifold X and B2 plus of X is greater than 1. Then if the first homology of X with Z coefficients has no two torsion, then we fix a homology orientation and we define a function which is called the Seiberg-Witten function of X. It is an integer valued function, and in fact it is a diffeomorphism invariant. And the domain is given in this way, it is this set. So we have the second cohomology classes of X, and they are mod 2 equivalent to the second Stiefel-Whitney classes of the tangent bundle of X. And such a second cohomology class K is called a basic class of X if the Seiberg-Witten function doesn't vanish at K. And we use this notation to denote the set of basic classes of X. And here there is a special moduli space, let me mention that. Let's say that we have G, this is a Riemannian metric on X, and H is an arbitrary closed real-valued self-dual 2 form on our manifold X. Then we have the perturb Seiberg-Witten moduli space denoted in this way, MXKGH, and it is depending on the class K and the Riemannian metric and H, and it is defined as the solution space of the Seiberg-Witten equations, and these are the two equations divided by the gauge group. So these equations are coming from physics, and our moduli space is the solution space of these equations. And moreover, let's say that the B2 plus of your manifold is greater than or equal to 1 and H is generic, and then the moduli space is a closed manifold in this case, and its dimension is given in this way. We denote it by D, and it is equal to this thing. And if dimension is less than 0, then it implies that the moduli space is empty. And in this case, our Seiberg-Witten invariant, or Seiberg-Witten function, vanishes at the class K by definition. And of course, if D is non-negative, then we have a definition for that function. But during this talk, I will not need that definition, so let me just skip this part. we only need this fact given here. And moreover, we have a nice formula. It is kind of technical. Let me just give the main idea. First of all, a simply connected smooth form manifold X is called of simple type if each of the basic classes satisfying this equality. And there is a blow-up formula due to Fintush-Allen's term. And let me just give the main idea. I want to consider the blow-up case. Let's say that I have a manifold X, which is of simple type. And this is the definition of being simple type. And let's say that I'm blowing up X at n points. So here n is a negative definite form manifold. Let's consider this as n connected sums of CP2 bars. And then the resulting manifold is X prime. Then the blow-up formula gives us a relation between the set of basic classes of X, these are here, and the set of basic classes of the resulting manifold X prime. This is the main idea, and this is a quite useful formula. And moreover, we also know how to compute the basic classes of the elliptic surface En, for n is at least 2, and it is again due to Fintush-Allen's term, and it is computational. And let me skip that part also. Now, I want to give the sketch of one of my constructions. On my paper, I have given various constructions of different symplectic form manifolds, and here I'm just giving one of them. And in each case, I have worked with different configurations, and each of these configurations are coming from different cubics, different pencils of cubics. So here, just one case. So this is a pencil of cubics in the complex projective plane. And for instance, here C1 is a nodal cubic, which is shown in blue, and C is another singular cubic. These are the members of my pencil. And another member is the union of the line L and the conic Q. So L is a line, so this is degree 1, and Q is a conic, its degree is 2, and their union is a member of the pencil. And in fact, this Q and P are the base points of my pencil. And the intersection multiplicities are given as follows. Here the multiplicity of Q is 3, and the intersection multiplicity here is 6. So they are adding up to 9, which is good. And also, base points means that every member of the pencil should pass through these 2 points. Well, we start with this cubic, this pencil of cubic, and from this pencil we obtain a configuration of IN singularities. First, I obtain a configuration of IN singularities in E1, which is CP2 blown up at 9 points, and then I pass to ENs. And here, actually, I get such a configuration inside the manifold E5. And by the way, this is a local picture. I'm not showing all of the singular fibers. There are many, there are other singularities around, but I'm just showing 3 of them. And this configuration is lying inside this manifold. And here we see an I6 singular fiber, an I3 singularity, and I2 singularity. And here each line you see, or each curve, these are irreducible components of the singular fibers, and these are all two spheres of self-intersections -2. Only this red curve here, it is a two sphere, but its self-intersection is -5, and it is the section, one of the sections of this form manifold. Well, then I start with this configuration, and then out of this I obtain specific plumbing. From this configuration, I do at certain points I'm doing symplectic resolutions and blow-ups, and then I obtain a star-shaped plumbing, which is denoted by U, and now it's lying inside E5 blown up at 3 points. And this is the graph for the plumbing. Actually, in this notation, each dot denotes a disk bundle over S2 of Euler number -3, for instance, and this guy is a disk bundle over S2 with Euler number -2, and they are plumbed together. And this is our configuration, or our plumbing. And then we apply star surgeries. From our manifold, we take out this plumbing, or if you like, we are taking out the neighborhood of the configurations of these spheres, and then we replace that by its filling V. And here V is a symplectic form manifold with boundary, of course, and its invariants are given in this way. And I call the resulting manifold T. And here then I show that the symplectic form manifold T is simply connected. It has an exotic smooth structure, and it is on the Noether line. And these are all computational. Next, I want to show that T is minimal. Minimal means that there is no -1 sphere inside the manifold. And I show that by working with the dimension of the Seiberg-Witten moduli space. First, I'm showing that only the top class, which is 3f plus e1 plus e2 plus e3 of this manifold, extends to T as a basic class up to sign. And in fact, there is a nice argument which says that, let's remember T is given in this way, and there's a nice argument which says that all of the classes can come from only this part. From the filling, there is no contribution. Therefore, I'm using this fact and I'm checking which basic classes of this manifold are extending to T. And I show that only the basic class extends to my manifold up to sign. Therefore, this shows that T has only one Seiberg-Witten basic class up to sign. And next, I show that T is minimal. Here, I prove that by using this fact. T has just one Seiberg-Witten basic class, and I'm also using the blow-up formula. And the proof is by contradiction. And if you are wondering, I can give more details during the conference. And hence, I showed the following. I showed that there exists a minimal simply connected symplectic form manifold T lying on the Noether line, and T is obtained by the UV star surgery. It has one Seiberg-Witten basic class, and it has an exotic smooth structure. So this was my sketch, and this is the result. And again, as I said, in each of my constructions, I have worked with different configurations, and I obtained different type of symplectic form manifolds. And I guess this is all I wanted to say. Thanks a lot for your attention. Please let me know if you have any questions, either by email or during the conference in the comments section. Just please let me know if you have any questions. And thanks a lot. Let me stop here.